for just a relatively small number of people, I think we're going to start the tour in any event. This tour is essentially going to look at water treatment at various scales and for various purposes. And it will touch on activity that's going on here in Israel and in some cases abroad. The issues that are dealt with are issues of both water quality and of water scarcity, and we'll address both, and we'll see what's been done in Israel to address both issues as part of this virtual tour. The tour is going to be divided up into essentially two sections. The one section will be on various efforts to take wastewater and to either treat it for recycling or to treat it to recover valuable resources from the wastewater, or to prevent health issues or issues of preventing of disease spread and how that fits in with dealing with the wastewater. And then the second half of the tour will be on various approaches to desalination, starting with a little bit of the history of how desalination got started here in Israel, and then moving on to various activities that are being done in desalination here in Israel and abroad. So I'm going to go ahead and open up the share screen. I'm going to have to move this down. So we're going to start with the issue, as I said, the issue of treating wastewater and how the treating of wastewater can be, instead of an environmental problem, can be an environmental resource. And we'll start with the talk of Professor Amit Gross, who will tell us about how the effluent from aquaculture can be a resource instead of an environmental problem.
אנחנו לא שומעים אותו. אנחנו לא שומעים את המרצה, אנחנו לא שומעים את הוידאו. אתם צריכים לסדר את זה דרך הזום, לסדר את זה שאפשר יהיה לשמוע דרך המכשיר שלך.
אני צריך לבטל את ה-share screen?
לא לבטל את ה-share screen, יש למטה איזשהו כפתור שמאפשר לך לבחור מאיפה השמע, ואתה צריך לבחור from this device או משהו דומה, אחרת אנחנו לא שומעים אותו.
I apologize to everyone, but apparently there's a problem with the sound. So I'm solving that problem now, and I'm going to do it so that everybody will be able to hear. So just bear with me a moment, and I'll get this to work properly. עכשיו, מה אני צריך לעשות? אני צריך לשים... אני יצאתי מ-share screen? אוקיי.
למטה, בסרגל למטה, באחת האופציות צריך להיות, אני לא זוכר בדיוק איפה.
כן, הוא פותח לי חלון, הוא כותב, you are share screening, אוקיי, עכשיו יש או pause share, יש remote control, יש ליד mute, כן. נכון. שניהם? כן. אוקיי.
Hello all. Thank you for joining us here at the aquaponic facility. My name is Amit Gross, and I'm the head of the Zuckerberg Institute for Water Research, and doing research which I may say would be called or termed waste to resource in various aspects. Here we came to one of the models that we're running, which is an intensive aquaculture system that is attached, or the wastewater from the aquaculture system is attached to a plant growth, to a plant bed, and I'll say a few words about that, and called aquaponics. So basically, when we grow fish for food, there is mainly one input, which is the fish feed. And the fish feed is being eaten by the fish, and about 30% is recovered by the fish flesh and muscles and so on. And the rest, 70 or 80%, is actually wasted into the water, potentially causing pollution, and contain a lot of energy and nutrients. So traditionally it was wasted. In recent years, we tend to recover these resources from the wastewater and treat the water as follows. So the ammonia that is being excreted from the fish, which is toxic to them, is being converted into nitrate in a nitrifying filter, which we can see just behind us. And the solid excretion is being trapped in a solid filter, in this case, a drum filter. The nitrate is being released into plant beds or hydroponic beds, where the plants take the nutrients up, and then the nitrate up, and then the phosphorus, and then the water can come back to the system. The solid waste, instead of wasting it, we dispose it here into an anaerobic reactor. In this case, it's a upflow anaerobic sludge blanket, where biogas is formed anaerobically, and this biogas is used for energy to run the system. The supernatant, the effluent from the anaerobic digester, contain a lot of ammonia and phosphorus because it's anaerobic and it's being mixed with the nitrate that came from the biofilter and go into the plant bed. So overall, what we are trying to do is to recover or fully recover the water, fully recover the energy that is wasted by the fish and run the system on it, and recover all the nutrients for the plant growth. So by that, we pretty much can say that we follow the water, food, energy nexus. One extra thing that we are doing in order to create a near zero waste unit, we take all the plant waste, roots and dead leaves and so on, and we introduce it into another biodigester, anaerobic biodigester, and collect even more biogas and more energy from the plant waste. So overall, as I said, we recover all the resources and do not leave any waste or discharge very little waste. And I guess with that, we thank you for listening and enjoy the rest of your virtual tour.
I want to thank Amit for his part, talking about the aquaculture and the reusing the effluent. The next stop will also be on effluent, but not from a fish pond, but rather from municipal effluent. And this is effluent that one of the things that needs to be treated in it are these materials called endocrine disrupting compounds, which you can see a whole class of them here. Includes pesticides from children's products, solvents, plastics, electronics, personal care products, antibacterial soaps, perfluorochemicals, which is an emerging one, which is a serious one. All of these compounds are relatively low molecular weight, so that what is usually used for doing membrane treatment of municipal wastewater is ultrafiltration. That would not be enough. Here you can see that ultrafiltration covers this area here. With viruses, it can stop, and bacteria, but it can't stop. It can't stop the much smaller molecules. The smaller molecules, the ones that have a molecular weight between 200 and 1,000, are the ones that are in the range of many of these emerging contaminants like the endocrine disrupting compounds. So for that, we need to use what is called nanofiltration. And a study that's now going on at Stable Care at the Zuckerberg Institute of Ben Gurion University and led by Dr. Oded Nir is shown in the next short clip. Here you can see the automated system. This is a computer-controlled filtration system, and the heart of it is this hollow fiber module, which contains nanofiltration membranes. They're a special developed membrane that was put together by the German collaborators at the University of Aachen, of Dr. Nir. And these fibers are capable of retaining small compounds, endocrine disrupting compounds, and other kinds of contaminants. In addition, this membrane can retain inorganic ions such as phosphate, and by concentrating up the phosphate, it's conceivable that it could be recovered. So if we take a look over here, what we can see is the feed container with the real effluent. And this is a concentrating system where it's running up. And as the effluent isn't concentrated, what you see here is a in situ camera that's looking at the suspension inside the municipal wastewater. And as the phosphate concentration goes up, it can precipitate as calcium phosphate. And that calcium phosphate could then be recovered as a nutrient, as something that could be contributed for fertilizer once it's been concentrated up. As I said, this whole system is all integrated with the computer control and computer registration of the performance of the membranes. You can see the performance on the screen here. This is the flow sheet.
Change to
and this is the flow sheet of the process. And now they're showing the performance. What you see here is the flux in these hollow fiber membranes, and here you can see the transmembrane pressure drop. You can see that for the time that they're running on this particular experiment, with the concentration that they've done so far, they've been able to run without any significant fouling, as the transmembrane pressure stays constant with the flux that's staying constant. So this is at the level of feasibility studies that are now being done in the laboratory, and we're now going to take you from the most let's say basic lab scale to the largest scale, and that is we're going to do a guided tour of the Shafdan sewage reclamation plant, which is the largest sewage reclamation plant in Israel. Treating all the water of the greater Tel Aviv area. And as we'll see, that water is being used, that water is then being used for agriculture here in Israel. Those of you who heard the lecture by Dr. Alon Ben-Gal earlier today, he explained what an important contribution this is to releasing Israel's agriculture sector from being dependent on fresh water. So I'll start the tour here.
We're standing in the center on a glass.
I'll just comment before he goes on that in actuality, this water is not used as potable water. If someone drinks it accidentally, it's okay, but they actually have it running through separate lines that are not potable water lines, but they're lines for using it for irrigation and agriculture. However, it is treated to a very high level, but it is not intended to be used as drinking water, but rather as irrigation water.
We'll talk about sewage and how on earth to take this disgusting thing and transform it to potable water. Picture it. There you go. Now I feel like the president. And as you see, the map of Israel, and we have Tel Aviv City. You've been to Tel Aviv before? So Tel Aviv City, and the city that surrounds it, the metropolis, that's what we call Dan region. And it's the center of Israel. Why do we call it Dan region? Do you know? So 3.5 million people in that region, and the biggest wastewater treatment plant in the Middle East, and one of the largest in the world. This is how it looks all about. Now beneath that region, 30 meters beneath the ground, we have a conveyance system take the solids out of the wastewater, we have the bar screens, the pre-treatment. Basically use huge cones that separate the solids from the water. This is how they look in real life. Soon, we'll see how they really work. This is how it looks. Very beautiful. There you go. There is the scum. Here's a close-up. And another one. Very romantic. And it all goes out to a big trash container. From a trash container by truck, or to recycling, or to the dumping sites. We cannot separate oils, fats, sand, or small stones in this fashion. And that's why we have the waste in basins. Basically, water canal. Water stands still, oils and fats, what do? Float. They don't go up, okay? It's just float. And sand and small stones, what do? Sinks and settle, very good. Then when it happens naturally, this blue grid goes, skims the fats and the oils out to a big fat oil container, and truck will take it to the nearby plant called Drylands. Drylands will recycle the oils and the fats to biodiesel, energy for the industry. The sand and the grit will be removed by small RPD's pumps, and then to the trash container. Finally, we can start purifying the water. Biological reactors. All the wastewater and then nutrient are here. And then we have pathogenic diseases, we have the ammonia, we have the good bacteria that digest. What will you do? This thing is actually separated to 3 stages: aerobic, anaerobic, and anoxic. With oxygen, without oxygen, and with certain levels of oxygen. To get rid of the pathogenic walls, and then the chlorine to kill some pathogenic bacteria. Today, 50% of the water that we drink in Israel coming from desalination. 31 desalination plants in Israel. The rest coming still from the aquifers and a bit from the Sea of Galilee. This is how we have water to drink. This is what we do here. So the used water we use again here to the agriculture.
Only agriculture.
Only agriculture. Any other questions? In other countries in the past, they didn't really have plants like this because they had a lot of water, or they didn't have water but they didn't have the money to do it. So these days, slowly, the world waking up and started to build wastewater treatment plants. In Europe, we have a lot of them, in the United States, some even in Africa, in China, Singapore, all over the world. Out of it, what? It was one of the first. It was one. 10 years ago, it was the largest in the world. Today, it's only the largest in the Middle East. A lot of Israeli companies going around all the time and building these facilities all over the world. These days, in Nevada, California, Australia, China, and Zanzibar, these days, all the time we're advancing. Yeah, they're getting the money or from the UN investments, or they have their own money, such as Nevada, California. They say. How much do we see every day? 370,000 cubic meters. 300 feet. Okay. How many indicators? We test a lot of things. I will show you the table right away. Who tests them? We test the water 4 times a day in every stage. Very important to us to know how it's working, if it's really working, really purified. Then you have the EPA, the Environmental Protection Agency or office in Israel, that also samples the water. Then we have the health department that also comes here and samples the water. And obviously we have inspectors from the city itself to inspect the water. Then, as I heard, the farmers themselves, when they get the water, they check it before they use it. So we check a lot of times. What exactly do we check? I will show you right now. Tables. I'll just show you a bit. The sand fields, the soil aquifer treatment, outside of this plant, from Rishon to Ashdod, 1,000 dunams. This is how it looks. And then this is how it looks inside. Going in, 400 days, 30 to 50 meters.
This soil aquifer treatment is the critical step that allows the water to reach the quality that's needed for using it for agriculture. The water is kept underground for close to a year, and during which time additional biological processes take place that remove the remaining contaminants. And then it's pumped out again, and what's pumped out is essentially the recharge water plus what's in the aquifer. There is research going on now to find ways to shorten this residence time or to either reduce the time for the soil aquifer treatment or provide other alternatives, because they're rounding out of fields that can be used for doing the infiltration and the recharge.
Material stays inside, then we pump it out. And now we're going to see the real plant and the real machine. Hope it's a good day today. Seems like it. We will find out soon enough.
There we are. I see you can smell it. Very nice smell. Inhale, exhale. Very nice. From here, warning this stage, and you can see the biological reactors to our left, to our right, and even in front of us. Aerobic, anaerobic, and anaerobic stages will deal with the pathogenic bacteria, with the ammonia. Okay, so this is settling basin 1 out of 12. What happens here? Here what you see, this is the secondary effluent. This is why it smells better. After 1 day, we have it here. At the beginning of the plant, we have 20 bar screens that will separate 40 tons of solids every day. Why do we have them again here? Because the pools are open. A pigeon can rest in peace here. So it takes the garbage out. So what do we see here? A settling basin. As we said, we have 12 of these. What happened to the sludge that we took out? 70% of the sludge will be returned to the activated system, to the biological reactors, the big pools with all the water in them. That's how we always have a lot of the good bacteria. 30% we need to recycle.
So that gives you a bird's eye view of the Shafdan plant. Today, Israel is recycling over 90% of its wastewater for agriculture, which is by far the highest extent of any country in the world. And as I said, that's why we're able to reduce the freshwater requirements of Israeli agriculture. Now we're going to look at the wastewater effluent, not from the point of view of agriculture, but from the point of view of epidemiology. And that's coming up in the next clip.
הניסיונות להתמודד עם נגיף קורונה הגיעו אפילו לכאן, למתקן טיהור שפכים לא רחוק מבאר שבע.
אנחנו דוגמים את השפכים כדי לנסות לראות אם אנחנו נוכל למצוא בהם את החומר הגנטי של וירוס הקורונה. ידוע כבר שהקורונה אפשר למצוא אותה בשפכים. היא נמצאה גם בצואה של אנשים.
באמצעות הדגימה הזאת ממי השופכין מנסים החוקרים מאוניברסיטת בן גוריון למנוע התפרצות מחודשת של מגפת הקורונה. אחרי שמחקרים קודמים הצביעו שנגיף הקורונה שורד בתנאים שונים, המחקר של אוניברסיטת בן גוריון בשיתוף משרד הבריאות מצא נוכחות של הנגיף במי השופכין של גוש דן, ובמיוחד באלה של בני ברק, מוקד התפרצות מרכזי. ולא רק זה, החוקרים מצאו גם דרך לטהר את השפכים.
אנחנו כרגע דוגמים שפכים מכ10-12 מתקנים בכל הארץ, ובמקומות מסוימים גם משפכים של בתי חולים וגם מצנרת ביוב עירונית בגוש דן.
זה הבקבוקים אחרי ההדגרה של לילה. הבדיקות האלה שאנחנו עושים ממקומות שונים בארץ בעצם מאפשר לנו זיהוי של מקומות ההתפרצות וככה לנתב את ההגבלות ואת ההנחיות בהתאם כדי שזה יישאר באותו אזור ונוכל לטפל בזה שם.
החוקרים כנראה לא קיבלו את ההשראה לטיהור מאיוב קרא, השר לשעבר, שטען כי קיבל מכשיר מיוחד לעצירת התפשטות הנגיף במים.
המכשיר הזה, מי שבעצם שותה את המים שלו, בחיים לא יקרה לו שום וירוס שיתגבר עליו, כולל קורונה.
יש, פתרנו את הקורונה, לא צריך לדאוג יותר.
מה שבטוח, פיתוחים יצירתיים כמו זה מנסים לחשוב עוד קצת מחוץ לקופסה בניסיון להתמודד עם הנגיף ולבלום אותו כמה שיותר מוקדם.
So, that's an example of where essentially wastewater can be a sign for doing epidemiological tracing, and that's the primary purpose for which that study is being done, and that work continues. So till now, I've been talking to you about various projects that are related to wastewater, either as a source of resources or as a source of information. Now, what we're going to do is go over to the subject of desalination, and actually I'll give you a little bit of history in the beginning. Essentially, desalination with membranes began in Israel in the 1960s. It was preceded by seminal theoretical work that was done by Professor Ora Kedem and the late Professor Aaron Katzir, who made the basic theory for the transport of salt and water through membranes. And there were two processes, membrane-based processes, that were looked at, both of which were examined in the mid to late 60s. The first process that was looked at was electrodialysis, in which you have the feed water coming into a chamber which is bounded by an anion exchange membrane and a cation exchange membrane. The electric field that's applied pulls the ions out into a concentrate chamber, which is adjacent to the diluent chamber, the product water chamber, and in this way is able to desalinate the water. Electrodialysis systems were developed and put into place at the Institutes for Applied Research, which was an institution which preceded Ben-Gurion University, and from that group came part of the Desalination and Water Treatment Department that is now part of the Zuckerberg Institute. The first system that was set up not too far from Midreshet Stable Care. So I'll go now to the next thing.
Modern day desalination in Israel began over 50 years ago in 1968 when an electrodialysis desalination unit was placed in Mashabei Sadeh, just 6-7 minute drive away from Stable Care, and the preparation of reverse osmosis desalination based on the invention of the late Professor Sid Loeb, who made desalination membranes inside 4 to 6 meter long half-inch tubes, which were prepared inside the system that you are looking at here. Here you can see a long cylindrical vertical channel in which the membranes were placed, and a polymer solution was drawn up through the inside of those membranes to put a thin polymer coating on the inside of the membranes in order that they could pass water and stop salt in the reverse osmosis process. Those membranes were then installed in a unit that was put in Yotvata. You can see the picture here of the plant at Yotvata, where they provided the first desalinated drinking water for this settlement in the Arava.
It's hanging up right now. So I think, just a second. Let's see if we can get this to. Okay, we have a problem with that particular film. I'll go on to the next one. Stop share, and I'll do share screen again. Okay, and what you see here is, let me just move this out of the way so it doesn't interfere. What you see here is a problem with nitrate contamination and salt contamination of groundwater in communities that have a intensive agriculture being done, industrialized agriculture, and communities of farm workers that are living on this land are then left with water that is not really fit for drinking, and they have a problem of obtaining a reliable source of potable water because of both the salinization of the groundwater and the increasing contamination of the groundwater with nitrate from the agricultural activity. So a system needs to be found to try to provide a solution for these communities. So you can see the reverse osmosis system that's is going to be used.
Flero is a novel smart RO system of compact design that can operate seamlessly in batch or wide salinity range, from brackish to seawater. This short video clip documents a recent field testing of Flero in the California San Joaquin Valley. Flero, along with its various sensors, including our newly developed nitrate monitoring system, were transported from UCLA to our field site. We reached the field site in about 3.5 hours. This field test site is a small water system. Fortunately, the well water is brackish level to well below the MCL, and with water salinity of about 50 milligram per liter in terms of total dissolved solids. This high level of permeate water purity and low salinity should allow, with blending, for the production of safe drinking water for this community. As is apparent here, all is well, and the guys can sit and relax with the smart Flero system doing the rest of the work. Our system ready to explore.
So this is a case where, again, there's nitrate contamination, and small remote communities need a system that can be matched to what their needs are, because of the fact that they have site-specific conditions, like there are septic tanks that limit what they can do, and regulatory compliance. So essentially, they need to handle these nitrate-laden systems that are being, these nitrate systems that are essentially, they get a high nitrate concentrate from the RO system, and they have to design it so that those high nitrates brine systems can be treated by their community septic tanks. So here you can see what needs to be done. They take the feed from the groundwater. Permeate is, of course, used by the household. The concentrate plus the household sewage together go into the septic tank. Here they undergo denitrification in the septic tank. And once denitrification has been completed so that there's not high nitrate levels, they can then discharge from the septic tank into a leach field. So in this case, they needed a high water quality, but also high recovery operations so that they wouldn't waste this precious resource. This required getting, this is one of the key things, is they had to get approvals. I'll just pull that back a second. Notice all of the different government agencies that they had to get approval from to be able to put this on site. So essentially what this is saying is that technology is not the only hurdle that you have to overcome with these kind of systems. You also have to make sure that you are interfaced with the correct regulatory agencies and know how to answer the questions that they have in the terms that are intelligible to them. So here you can see the system. I'm just going to pull it back again a second. Here you can see this is a system that can produce 22 cubic meters a day. It starts at 600 to 1500 part per million of TDS. The nitrate level is quite high. It's 56 part per million as nitrogen. Okay, that's not as nitrate, as nitrogen. So that's quite high. What they did was to develop the system and make it an automatic system they knew would work properly, is they developed their own proprietary nitrate sensors that could monitor the nitrate both in the feed and in the permeate as a way of determining that they were getting the performance that they needed. Okay, so that covers the flexible RO system. This is a system for small communities where you need something that's distributed. Those of you that heard the lecture of Professor Amos Winter in the Water and Agriculture session earlier today, I heard about the same kind of challenges that system was designed to cover. This system is equally designed to cover a distributed system that can be deployed where there are small communities that need improved quality water from the degraded water sources that presently exist. So now we're going to go from the very, very small to the very, very large, in which we're going to look at what has been the world's largest seawater desalination plant, which is located here in Israel.
Welcome to a 360-degree tour of the Sorek desalination plant here in the heart of Israel. Sorek is the world's largest seawater reverse osmosis project, providing enough water for 3.8 million people per day, meeting 20% of Israel's water demands. Delivered by IDE Technologies and Hutchinson Water International, Sorek has been awarded for multiple engineering innovations, including the use of 16-inch vertical membranes. So join me now for a 360-degree tour. Here you can see the Palmakim beach, located 2 kilometers from the Sorek site. Using pipe jacking techniques, IDE Technologies was able to connect the sea to the desalination plant without disturbing the Sorek National Park. Moving on to the pumping station, here you can see the diameter of the pipe used to feed the plant. A total of 7 pumps are installed here, pumping 54,000 cubic meters per hour of fresh feed water. For the next stage of the process, you can now see the pre-treatment, an essential line of defense to protect the membranes. Dual media gravity filtration acts as a barrier to prevent the seawater reverse osmosis membranes from fouling. Next, we have the heart of the Sorek desalination plant, reverse osmosis. Here you can see the innovative use of 16-inch SWRO membranes. Around 10,000 modules are used with 8 membranes per vessel. By using the membranes vertically, it has led to a minimized plant footprint, lower installation costs, and shorter pipes, reducing the amount of high-grade metals needed for the process. Brine is a byproduct from the seawater desalination process. It's a concentrate brine being mixed by a diffuser with seawater before being returned to the sea at a depth of 20 meters. An online monitoring system working 24 hours a day ensures that all environmental regulations are met, in the process minimizing any impact on the sea. Next, we have the remineralization process. Following membrane filtration, which takes out all the salts from the seawater, minerals such as calcium, essential for our health, are added back into the water. Limestone treatment, followed by final disinfection, helps to achieve final water quality. Finally, we reach the brain of the operation, the control room. Although the plant can produce 624,000 cubic meters per day of potable water, using a fully automated process means a very low number of plant operators is needed. The design of the plant, together with operation and maintenance know-how, has enabled IDE Technologies to change its output depending on the time of the day.
So we hope you've enjoyed the 360-degree tour here at Sorek in Israel. Sorek has proven it's possible to deliver large-scale, environmentally sensitive seawater reverse osmosis despite facing a challenging site footprint. Together with the Ashkelon and Hadera facilities, also provided by IDE Technologies, Israel now provides 70% of its water through 5 desalination plants. Thanks for watching.
Okay, so that concludes the virtual water tour. If anyone has any questions about something that they saw in the tour, I'll try to answer what I can. Okay, thank you all for joining, and have a nice evening or a nice morning, depending where you are. And we'll see you at the other sessions later on. Take care. Bye-bye.